Geochronology is a study of time in geology. In our textbook, it is chapter 7. I think it refers to it as geologic time. Geologic time or deep time. That's another phrase we often hear associated with geochronology. Sometimes even the abyss of time, because looking backwards in time from a geologist's perspective is so much deeper, so much farther than our short human lives, that it becomes a challenge to reconcile the numbers that we're going to talk about. Now, so geochronology is dates and ages. It's how fast things occur, which is super important because it helps us understand process. When did something occur? Then what happened next? Or something occurred. How fast did it occur? All that is within the chron, the clock of geochronology. Within geochronology, there's two main fields. One is called relative dating, and the other is absolute dating. And absolute dating is probably the most powerful of the two. This is the real number. Real number. We could say quantitative. Quantitative. It's like I'm 42 years old. Well, actually, I'm 42 years old in 270 days. This is a real hard number. A crystal could be 101.2 million years old. That is something that is found through absolute dating. Where relative dating is relative to something else. What came first, second, or third? I'm the oldest sibling. I have two younger siblings. This could be an example for like science. You could say something like the Jurassic time period is older than the Cretaceous. It's relative to something else. Now, as we get into this, I want to introduce, we're just going to start with the Earth. The Earth is 4.54 billion years old. That's like the first thing I just want to say in this lecture and written down. Earth is 4.54 billion years old. Right? We live for 100 years tops. How can we conceptualize 4.54? I don't even know. The Earth started. A lot of times we think about the Earth as this pale blue dot in outer space. It was actually 4.54 billion years ago. It was probably a pale orange dot. There was no oxygen. There was no water. All these things have happened since life becomes mountain range, tectonic start. All this is happening in the 4.5 years since it started as a pale orange dot that condensed out of the dust of a spinning solar nebula. This is just our starting point. I'm going to go ahead and put that on here, although it could be built in another lecture. Condensed from dust of a spinning solar nebula. And one reason to put this here at the start is it really challenges a worldview. What started it? What came before? Right? Depending on what culture and what religion you're a part of, this can be very controversial. It can be accepted. It's fascinating. It's interesting. So hopefully this lecture gives you some tools to understand our planet and yourself within this world. To help us frame this 4.5 billion years since the beginning of time, we use something called the geologic time scale. It's a tool. I'm going to go ahead and scale geologic time. So I'm going to insert it first, and then we're going to talk about it for a second after that. So when I talk about a geologic time scale, this is the picture that I want you to have. Basically, we go from today, and there's a name for today. It's called the Holocene. And then you go backwards in time to the beginning of Earth. There it is, 4.5 years ago, and a time period we call the Hadean. Hades, like hell, hot, lifeless. And all these other chapters throughout history have a story to tell. They have tectonic events occurring, magmas are crystallizing, life is maybe forming or dying out. And so within this geologic time scale, I want you to learn it as a tool to organize the immensity of time. Tool to organize the immensity of time. And we in geology use it all the time for that way. Each one of these you could think of as chapters. So tool to organize the immensity of time into chapters. And because of the movie with the dinosaurs, many people have heard about the Jurassic time period. Maybe some people have heard of the Cretaceous. Some of these other ones you've never heard of before at all. And you don't need to memorize them for this class. Later class periods, you're absolutely going to need to memorize this sequence and these big dates associated with each of those chapters. Most of these are defined by some kind of significant geologic event, like an extinction. That's what ends a chapter or starts a chapter. Now, the meat of this lecture is I want to get into absolute dating and how the process of absolute dating works. It's going to be the topic for next lecture as well. But I'm going to go through 1, 2, 3, 4 here as the building blocks for absolute dating. Building blocks for absolute dating. How can we say that the Earth started 4.5 billion years ago or that the dinosaurs went extinct at 66? Well, to get to that, you've got to be with me here with absolute dating. And this concept really that it's based upon is the concept of radioactive decay. And to get to radioactive decay, we need to start with the atom. So number 1 in this quick list of 4 is that there is an atom. And we're just going to introduce that there is an atom. The basic atom has protons, neutrons, and electrons. And the protons, I know this is high school stuff, this is middle school stuff. The protons determine the element. They have a mass of 1. A neutron is just mass. It's neutral. And then electrons determine, right, they balance off the protons. But if we were to sketch, let's say, a helium atom, we could have a nucleus. And in the nucleus, there are protons and neutrons. We'll have 2 of each. Have a mass here of 4 equals 4, because that's the sum of the p's and the n's. And then there's going to be 2 electrons in the outer orbitals. This is just an example of helium. Now let's make this more complicated. Beyond the basic atom, there are isotopes. So we can say something like isotopes exist, or we'll just define isotope. And an isotope, let's guess you could say an element can have a different mass. Element may have different masses. Now we can't change the proton to have a different mass, because if you change the proton number, you change the actual element. So this has to be done by having different number of neutrons. Different number of neutrons. And we can do an example of this. This is a relevant example. Uranium-235 and uranium-238. These are both radioactive isotopes of uranium. They have the same exact number of protons, but they have different number of neutrons. Uranium-235 has 143 neutrons. And uranium-238 has 146. Okay, so same number of protons, different number of neutrons makes something an isotope. Some isotopes are stable, they do not undergo radioactive decay, and others do undergo radioactive decay. So that was number 2. Now we're going to go to number 3 in this build of the concept. It's going to be radioactive decay. And the concept of radioactive decay is that some isotopes have unstable nuclei. Some isotopes have unstable nuclei. And what they're going to do is they are going to lose energy in the form of a particle, an alpha decay, a beta decay, or a gamma decay. And oftentimes radioactive decay is considered bad, but it's not bad. It's an opportunity to exploit for geology in order to do geochronology. So radioactive decay is good, it's critical, it's important for this study. And so there's 3 different types. There is alpha decay, and alpha decay is often given the symbol alpha, and it is the loss of 2 protons plus 2 neutrons. So anytime an alpha decay particle occurs, you drop your atomic mass by 4, and you drop your atomic mass by 4, and you drop your atomic number, your element, by 2. So this will like actually change the element and the mass. There is beta decay. It's given the big beta symbol, and it is the decay of an electron, or so an electron is lost. And then finally there's gamma radiation, which doesn't, well, anyways, we're not going to worry about it right now. Those are your 3 different ways that we can have radioactive decay of an isotope. And the rate at which this radioactive decay occurs is called a half-life. So number 4 is half-life. We're going to say time for the radioactive parent to decay into a daughter. That's the way we should say it. And it's time for exactly half of that parent to decay into the daughter. So we're going to say time for 1/2 of parent isotope to decay to daughter. There are so many different isotopes that have different half-lives out there. In fact, it's 55 orders of magnitude are reflected in nature. Some are picoseconds and some are billions of years. And if you find one that is appropriate for geology, maybe you can date a rock. Another concept under half-life that is important is the symbol. Is this symbol right here. This stands for lambda. Lambda. And lambda is related to half-life, where half-life, I'm going to give it the symbol T half, equals the natural log 2 of lambda. And so sometimes in the equations that we're going to use, the information is going to be provided for you in half-life, and sometimes it's going to be provided for you as lambda. So you just want to be able to be comfortable with the 2 of those. And so watch what happens when half-life occurs. We're going to draw a graph here, and this graph is going to show the amount of parent for different half-lives. So here's T to the 1/2. And so here is 1 half-life, here is 2 half-lives, here is 3 half-lives, and we'll end at 4 half-lives. And I guess we're going to start with 100% of parent is happening at initial crystallization. But time progresses, and after 1 half-life, that means 50% of the parent will have decayed to daughter. So at 1, it's 50. At 2 half-lives, it is another half is gone. So what's 50 divided by 2? Well, it's 25. So here we go, it should be here. So after 1 half-life, you're at 50% remaining. After 2 half-lives, you're at 25% remaining. After a 3rd half-life, well, it's half of 25, so it's 12.5. And after another half-life, it's half of 12.5, so it'd be 6.25% of the original materials there. And so the parent is decaying in its concentration through time. What's the daughter doing? Can you guess? After, well, of course you can. After 1 half-life, this daughter started, let's say, at 0. After 1 half-life, it will be up to 50. And then it'll go up to 75. And then it'll go up to 87. This is the ingrowth. We call it radiogenic ingrowth of a daughter and the radioactive decay of our parent.